seminar speaker, Lee Samuel Finn, who is a well-known expert in the field of gravitational wave science. He did his PhD at Caltech and is now a professor at Penn State, where he heads the gravitational wave astronomy group there. And he will be talking today about some of the work that he and his group are involved in.
Thank you. Does it sound okay?
Yeah.
Okay, excellent. So this is kind of interesting. Let me not say it's an interesting talk. You'll judge that afterwards. But it is maybe a little bit off the beaten path, because I'm largely not going to talk about details of research in a specific area, but I'm going to talk about trying to imagine how we will do research, or how to best do research in a new area of gravitational wave astronomy. Much has been made, certainly, of the promise that gravitational wave detection has for astronomy, but little has actually been done in imagining what the useful ways of thinking about gravitational waves and gravitational wave observations are from the perspective of an astronomer. To date, all the work that has been done has really focused principally on detecting gravitational waves. But as you know, there's a long way to go between detecting photons and actually doing astronomy with those observations. And my focus over the last several years has been principally on the question of what are the productive ways for thinking about gravitational waves, thinking about gravitational wave telescopes, not detectors, but telescopes, and thinking about gravitational wave observations, both by themselves and in concert with other observational modalities for the purpose of doing astronomical science with those observations. And what I'm going to tell you about is, in some sense, work in progress towards envisioning what gravitational wave astronomy may be in the future, after we have detected gravitational waves, and when we are confronted with observations and want to try to interpret them, to actually do astronomy with those observations. So before we get into it, I want to remind you of a maxim that I heard first ascribed to then General Dwight Eisenhower, which is that that when you are about to engage in battle, plans are nothing, but planning is everything. That is to say, what will come about and how we will in fact do gravitational wave astronomy may very well be very, very different than what I talked to you about here today. But what I think will be, nevertheless, I think that what we'll talk about today will be valuable in informing that future. So we'll talk about some different things. One is, how do you think productively about gravitational waves and their propagation and the relationship to sources? We're talking now about instrumentation and observations. How should we think about gravitational wave detectors? What, in fact, do they detect? And understanding what they detect and how they detect it, how can we use that information to design and build better gravitational wave telescopes? And when we say better, of course, we've immediately made a value judgment, and so we'll have to talk about what means better for our purposes. Better for one person's purposes, or not better for another's. And then, if given a telescope, how should a attack operate? That is, not in the political sense of the word, but rather, how do you look at the capabilities of a telescope and say, this is the best way to use it. This is the best way to arrange my observations to take advantage of the capabilities of the telescope. So again, it comes back to this question, how should we think about telescopes? And it's the flip side of how can we build better telescopes? How do we make the best use of the telescopes that we have? And then finally, a few words on analysis. How do we use our observations to do astronomy? So let's first talk about thinking about gravitational waves. It is what you learn in every graduate or undergraduate course in general relativity, that, well, gravitational waves are a metric perturbation. However, I will tell you right now that there is no such thing as a metric perturbation. I can make a metric perturbation by changing my coordinates. I can make the metric perturbation at any point in space-time, any line in space-time, go away. There is no physical thing that is the metric perturbation. So to say that we detect a metric perturbation is definitely not a very useful way of thinking about gravitational waves. It's like saying, it's actually worse in many ways than saying that, well, we don't detect electric and magnetic fields, we detect the vector potential. It's a very useful mathematical tool, and it can be related to something physical, but it is not in and of itself physical. So if we're going to think about gravitational waves as astronomers, we want to think about something that is physical. So the question then is, what is that thing? So let me start by introducing you to the orange. The orange is our model of a space-time with gravitational waves. The orange has a mean curvature, and it has, on short scales, dimples. That is, short-scale curvature fluctuations in it. The short-scale curvature fluctuations are, in the context of general relativity, what we term gravitational waves. An interesting thing, because of the nonlinear character of gravity, is that it's very difficult in an arbitrary circumstance to make a clean cut between your background space-time and gravitational waves. You need some kind of multi-scale situation to let you make that distinction. In the case of general relativity and gravitational waves, we need a background curvature on long scales, and we need curvature fluctuations on short scales. When we have that situation, the background curvature relative, or the short scale fluctuations relative to the background curvature are very, very much less than 1, then we can usefully and productively talk about gravitational radiation. Now, how is it that gravitational radiation operates in this way? Well, if we didn't have the dimples, if we didn't have the gravitational waves on our orange, and we were to draw straight lines on it, you can think about straight lines as photon trajectories here. The photon trajectories would be rather smooth, and they would follow the curvature of the orange, the background curvature of the space-time. However, we also have these short-scale fluctuations in the curvature. And because of those short-scale fluctuations, that trajectory varies. It scatters, if you will, off of those short-scale fluctuations. And it is that scattering off of the short-scale fluctuations, this is still, in the context of the orange, a straight-line path. But now it is a straight-line path that is sensitive not just to the long-scale curvature, but also to the short-scale fluctuations. It's one that shows these variations. The distance along the path, obviously, is different. And that difference is a large part of what we end up measuring. Now, you can characterize in space-time the curvature of this perturbation to the long-scale background in terms of two quantities, two tensors, that have the character in the context of tensor gravity that an electric field and a magnetic field have in the context of Maxwell vector electromagnetism. So we talk about an electric part of the overall curvature and a magnetic part of the overall curvature. And these are defined usefully in terms of observer congruences. They are fully physical things. You can measure them. And any observers who set out to measure the electric and magnetic parts of the curvature will reach the same conclusions as to the overall value of these, in the same way that any two observers who measure electric and magnetic fields will agree on the overall Faraday, the overall combination of electric and magnetic. So will any two observers who set out to and actually measure the electric and magnetic parts of the curvature will agree on those. Now, from this, we can begin to see how it is that gravitational wave detectors operate. So if we imagine a metronome following this trajectory in space-time, time up, space over, it is emitting pulses, sounding off at very evenly spaced moments of time. And we have a receiver over here. And space-time, is flat everywhere, but in between the two, there's a lump of curvature, if you will. Well, successive light rays traveling from the metronome to the observer travel the same distance, and so the elapsed time between emission of successive pulses and between observation of successive pulses is the same. At a certain point, however, a pulse in traveling from the emitter to the detector has to climb this mountain. That's traveling at the speed of light. It's traveling at a constant velocity. And so, for this particular kind of curvature, it takes longer to get there. There is a fluctuation in the time of reception of these pulses. Afterwards, you no longer have that extra path distance, and now the amount of time is shorter. The introduction of this curvature in between the emitter and the receiver leads to the fluctuation. Notice that there is nothing special going on here, and there is nothing special going on here. If we were talking about a metric perturbation, we would end up in some particular gauge talk about things that are happening on this world line, and perhaps things that are happening on this world line. But if we think physically, what we see is that it's not what's happening on anybody's world line. Rather, what we're seeing is the effect of propagation through the intervening space. Gravitational wave detectors measure things that are happening inside them in this way. And we'll see the significance of that in a little bit. So this, in fact, this illustration here is, if this was a pulsar and this was a radio telescope on Earth, this is how pulsar timing works. It's all about what's happening here. There's no such thing as a pulsar term. There's no such thing as an Earth term. It's about the curvature in between the pulsar and the Earth. If we were to reflect this back, so that we had the pulse arriving back, just put a mirror here, we had the pulse arriving back here, and we had another pulse heading out in another spatial direction and coming back, and we were to recombine them in an interferometric sense, then what we would have would be something like LIGO, an interferometric detector. It's the same thing. And again, what you end up measuring is curvature in the interior of the detector, or curvature fluctuations in the interior of the detector over time. Pulsar timing we already talked about. Now, one of the advantages of talking about gravitational waves in terms of curvature and in terms of these E and B is that, in fact, you can cast the full nonlinear Einstein equations in Maxwell-like form. That is, there is an equation that looks like divergence of E of the electric field is equal to something that involves the energy density of a source. The divergence of B vanishes. The curl of E is minus the time derivative along the congruence of E, and similarly the curl of B, you've got the equivalent of the displacement current here. Now, here I've specialized the equations to Minkowski space, and I've made all of the observers then relative rest, which I can do in Minkowski space. If I wanted to be fully nonlinear, and I've linearized the equations, if I wanted to be fully nonlinear, there are some additional source terms that show up in different places, most of which have to do with what you would call the relative motion of observers that are measuring the fields. And there's nothing special about that. I know two observers who are at motion with respect to each other are going to have a different sense of what is E and what is B. And that's all that's really going on here. In fact, if you were to replace E and B with the real electric field and the real magnetic field, these equations would basically be exactly the same, except for that term. So these equations are also Maxwell's equations in a curve space, except general relativity is an additional term over here. So there's a very useful way of thinking. There's a very useful set of analogies that one can develop if you focus on curvature as your principal quantities for thinking about gravitational waves. Finally, if we want to come back to the something useful like the dipole formula in electromagnetism and the quadrupole formula in gravitational wave studies, it turns out in the limit that we usually work in, the only difference between the quadrupole formula for the gravitational wave curvature electric field and the metric perturbation is in TT gauge, where it exists, is basically two time derivatives and a minus sign. So you don't lose anything, but you gain a lot in explanatory power and interpretive power. There are some other useful realizations that arise when you think about curvature fluctuations and some phenomena that are perhaps odd or difficult to think about in gravitational wave studies. One of them is so-called gravitational wave memory. There are two kinds of gravitational wave memory. One ends up with what is basically a linearly growing metric perturbation, which, if you think about it in terms of a metric perturbation, you say, well, I can't have a metric perturbation that linearly grows because I know my theory is broken down at that point. In this particular case, what you see is that what this really is two observers traveling along geodesics, straight lines. Neither one of them feels a gravitational wave because it doesn't do anything to them, but rather what is happening is that as the wave passes, there is a relative velocity that develops between the two observers. Space-time is flat. Before and after, nothing really has happened at all, except they have developed a relative velocity with respect to each other. It's just geodesic deviation. You can even argue then whether or not it's a gravitational wave phenomenon. And that is distinct from what you might term as a curvature memory, where there is actually a difference in the background curvature before and after the gravitational wave burst passes through your detector. There is a real difference in the space-time before and after. And so, for example, if you've got a binary black hole merger, you have, pardon the pun, two holes collide, and the final hole is less than the sum of its parts because energy has left the system. The energy leaving the system is related to an overall change in the curvature. And so you have a very measurable difference in the curvature outside the binary before and after the gravitational wave has passed. Now, if we want to think about gravitational wave telescopes, we've already seen some aspects of that in how gravitational wave telescopes work. Probably the most useful paradigm for thinking about gravitational wave telescopes is to think about radio telescopes. And this is because the nature of the observations, we make observations both at wavelengths that are long compared to our detectors, so we're in the small antenna limit, and we make observations at wavelengths for some antennas that are at wavelengths short compared to the size of the antenna. Pulsar timing is an example. The observations we make are phase sensitive. The signals that we're looking at tend toward the narrow band. Mostly what we're looking for, the kinds of sources we're observing or anticipating observing, are narrow band compared to the baseband frequency that we're operating with. And so there is a lot of parallels with the way radio telescopes, when you think about radio telescopes, the kind of observations that they make. You can talk about effective aperture, you can talk about a gain pattern, a front-to-back ratio, half-power beam width, and the like. You can talk about impedance matching to the space-time. These all become useful concepts, particularly when you talk about designing a gravitational wave detector and making choices in how you're going to instrument your detector to turn it into a telescope. And you always have choices that you can make. There is, however, one thing that is very unique about gravitational wave telescopes. There is no such thing as a point detector of gravitational waves. I can take an electron, and it's a point detector of electromagnetic waves. I can measure the acceleration of the electron. Okay? Because of the equivalence principle, essentially, there is no way for me to measure a gravitational wave or to measure the curvature fluctuation unless I have something that has a physical extent to it. That extent could be in time, it could be in space, it could be in both. But it has to have a physical space-time volume to it. Otherwise, you can't measure anything. And it's in this sense that we talk about measuring the curvature inside the instrument. The instrument has to have a finite extent to make that measurement. That having been said, in the limit where the size of the detector is very large compared to a wavelength of the radiation, or you're dealing with plane waves, you can't make a point detector-like approximation. Now, how this point will come into play in terms of how it will break the analogy here is something that I'm not in a position to give a good back of the envelope or off-the-cuff explanation or example of. But it is a very important point, and it can and has led to different kinds of mistakes in talking about gravitational wave detectors in the literature. To see how you have different choices that you can make, we'll talk about ground-based detectors, space-based detectors, and pulsar timing. One of the things that is kind of key here, ground-based detectors are of size meters to kilometers. For bar detectors, it's meters. For interferometers, it's kilometers. The wavelengths that you're talking about measuring are on the order of 10 to the 3 to 10 to the 5 kilometers. So you're definitely in the small antenna limit. The detectors are small compared to the wavelength of radiation. Space-based detectors that have been proposed, like whatever LISA is currently being called, have a size that's more on the order of 1 million kilometers. The gravitational wave radiation wavelength that they're sensitive to is from a fraction of that to several times that. So they operate in this intermediate regime. It's not a regime where you can say that these are quadrupole antennas, but it's not a regime where you have a lot of complications, or you can do a lot of imaging, as we'll see. Pulsar timing is particularly interesting in this regard. It's far off in the other direction. The size of a pulsar timing telescope is the distance from Earth to a pulsar. So we're talking about kiloparsec size, galactic scale gravitational wave detectors. The radiation wavelength, on the other hand, is on order light years that you're measuring. That's frequencies of 1 per several years. So we're very much in large antenna limit, and that has significant effects on what we can do and how we have to go about doing it with these detectors. One of the things that you want to do as an astronomer, if you can, is you want to image. When we're dealing with ground-based detectors, when you're in the small antenna limit, imaging basically means that you've got to take many detectors, widely separated, and synthesize an aperture. But you can do that in radio astronomy. That was done a long time ago. The basic electromagnetic antenna element is the dipole. You space around a lot of dipoles. In the case of gravitational wave, the basic gravitational wave antenna is a quadrupole antenna, and you image by interfering multiple basic envelopes, signal-to-noise ratio XX. That is probably, for this figure, a signal-to-noise of about 11, a gravitational wave burst. And in a network of 5 detectors, you can actually locate the source to a relatively small area on the sky. So this would be the 99% contour. You can see that black area here. And this is basically by synthesizing an aperture from the observations made at many different telescopes. Doing the aperture synthesis much the same as you would in radio astronomy. In pulsar timing, you image more directly because your antenna now is many wavelengths in size. And so you are very sensitive to the direction, to the source, relative to, in this case, the pulsar to Earth baseline. If you look at the response of a pulsar timing array, the response breaks up nicely into an amplitude, which is, thinking in terms of the metric perturbation, h over the frequency of the radiation, a purely geometric factor, wave propagation direction k, direction to the pulsar n hat, and then a piece that depends also on geometry, but is also frequency and detector size dependent. And in this particular case, this factor is on the order of 10 to the 3 for a pulsar at a 1 kiloparsec distance. So the response of the detector is very strongly dependent on the wave frequency, on the source location, and on the pulsar distance. So you can, in fact, image in a very different way. You still, in fact, want to work with multiple detectors, but you can do your imaging in that way. If you've got a telescope like this, or like any one of these, a question arises, how do you make the most of what you've got? And so that falls under the context, if you will, of strategy. And take a moment just to talk about what strategy is. It's a plan of action to achieve a vision. Okay? A standard textbook management 101 definition of strategy. So you have to ask yourself, what's the vision? What am I trying to accomplish here? And then what actions do I take to realize it? How do I build my detector? How do I allocate my observing time? What sources do I choose to observe? And you get your resources and you follow your plan. So the first question then is, what is it that I'm trying to accomplish? What are my priorities? And there can be many different kinds of priorities. And they can be in conflict with each other, as we'll see in a moment. My priority might be to make the earliest possible detection of gravitational waves. My priority might be to have the greatest effective bandwidth for my detector. My priority might be to be sensitive across the largest fraction of the sky that is possible. My priority might be to any source that I can see, I want to be able to do the best possible job of localizing it. I'm willing to give up seeing some sources in order to be able to localize best those sources that I see. I might want to learn the most about the radiation or the sources. I might want to, for example, resolve the wave polarization. And talk about some of these. In particular, we'll talk about localization and the science associated with it, ability to resolve wave polarization, the science associated with it, and the question, obviously, of earliest detection, and see how they can be in conflict with each other. So let's talk about those questions first in the context of ground-based interferometers. So I want to emphasize that you've always got choices that you can make. In the present situation, we're talking about putting a large interferometer in India. It's a greenfield site. We can orient that detector any way that we would like. So we can choose to orient it to do the best job for, say, the greatest survey volume, which amounts to saying I want to maximize, or I want to have the earliest possible detection. I want to be able to see the largest volume of space that I can. And I can also say that, well, I don't know when or if that LIGO India detector is going to come off. Something could go wrong. It could be very long delay. So I might first say, well, I'm trying to decide between putting a third interferometer at the Hanford Observatory or putting the third interferometer in India. Well, your best choice, if you want to have the best survey volume, detect gravitational waves the soonest, is to put that third interferometer at Hanford. Forget about India entirely. You will maximize the volume of space that you observe at a fixed signal-to-noise ratio, and you will observe then more sources, which means that you'll observe sources, your first sources, sooner. For an India sighting, so you can't really see this green curve, but it represents the variations in the volume of space actually this blue curve, is variations in the volume of space that you observe relative to keeping all your detectors, or relative to keeping both detectors at Hanford, which is 1. You lose about 10% of your sources if you put an interferometer in India, and there's a negligible fluctuation depending upon the orientation of that third interferometer in India. It amounts to 4%. But you basically lose 10% of your sources as soon as you put that detector in India.
So that line assumes that the Indian detectors goes online at the same time as the other detectors?
That's right. Once you've got all the detectors operating, the volume of space that you survey is going to be about 10% less than if you had all the detectors operating with 2 of them at Hanford. Okay? It's a choice.
Intuitively, why is that?
Intuitively, it is because it's the inverse square law, basically, or it's volume to. I should say, really, it's volume. If I can observe twice as far in a given direction, then I get 8 times as much volume. Whereas I can observe not quite twice as far, but over a larger area, and it's not the same. So really, that's intuitively what it's all about. If I add the Japanese detector, the Kagra, then, well, I do a little bit better. I have more interferometers. And the advantage to orienting the India antenna, there's a slight advantage to 40 degrees east of north. These are different, but the advantages are really negligible. There are going to be many more things that contribute uncertainties much greater than that level. If, on the other hand, I am interested in resolving the polarization of my gravitational wave sources, so I'm interested in doing source science with my observations, the story is very, very different. Then, LIGO only, there is, well, if by LIGO only I mean including the LIGO India detector, there is a major advantage to sighting the Indian detector with an arm 21 degrees north of east. It's a very significant advantage to sighting it there. And if I include also the Japanese detector and Virgo, then there is a major advantage to 25 degrees, or 25% advantage, 12 degrees north of east. So there's a significant orientational advantage, and it differs if I think that I'm going to be operating basically only the LIGO detectors, including LIGO India, or if I want to make a decision to optimize so that I'm including also the Japanese and the Virgo detector in my eventual network. So you do have choices that you can make in the sighting of a green field interferometer. The other thing to note, and it's not really coming out terribly well, there's a green curve here. And that green curve is just India, Hanford, and LIGO interferometers. And the blue curve, which the green curve is India, Hanford, Livingston, Virgo, and Japan. The blue curve is just India, Hanford, and the Livingston LIGO detectors. And the important point here is that a good choice, your good choice in the case of just focusing on LIGO detectors is better than your bad choice for all 5 detectors. So the choices really do make a difference. You can add 2 more interferometers to your array, but if you've made the wrong choice, you can be worse than if you had just made the right choice with 3 interferometers. LISA, another example where there is a choice to be made. In this case, a not necessarily obvious choice. LISA, you can ask about where are you going to see most of your LISA sources. Most of your LISA sources are going to be white dwarf binaries. They're going to be concentrated in the direction of the galactic center. So you can say, I want to optimize LISA to detect sources in the direction of the galactic center. Now, I don't have a lot of choices with the orbit of the LISA satellites. That is, it's got to be 60 degrees inclined with respect to the ecliptic plane, and so on. It's going to be a certain degree, a certain number of degrees ahead or behind the Earth. You could make a choice with that, but it's a lot of money. What you can do, however, is choose when you're going to launch LISA and what, within those parameters, where is the Earth relative to the Earth-Sun vector relative to the Sun galactic center vector. And that turns out to be a very important choice. In the case of LISA, choosing the initial orientation of the LISA satellites in their orbit makes about a 20% difference in the ability to localize sources in the direction of the galactic center. So if you were to rotate this constellation by, say, 20 degrees, you could make a very significant difference in your ability to detect or to characterize where sources are, to image, if you will, the gravitational wave sky in your principal sources. Again, there's a choice that you can make, and it makes very little difference in your ability to detect the sources. Very little difference in total signal-to-noise ratio, but a very large difference in your ability to localize the sources on the sky. In the case of pulsar timing, there's also choices that you can make. This is one where you're really building a detector. In the case of pulsar timing, if you add more pulsars, basically you increase the effective aperture of your telescope. That's the first thing to notice. So you'd say, I always want to add more pulsars. I don't care where they are. But if you look a little deeper, right now most of the pulsars that we know of are in the direction of the galactic center. Not surprising. You look, if you're looking for pulsars, you look where there are most of them, and that's where then you'll find them. That's really good for a large survey volume for the reasons that we discussed. If all the pulsars are in the same direction, then you're going to look very deeply in a single direction on the sky. If, on the other hand, I want to resolve the polarization of the radiation that I see, I need pulsars that are out of the plane, out of the galactic plane. Or really, I need pulsars that are away from either the direction to the galactic center or the anti-center direction. So I need things that are out of the galactic plane then. So I will, and then the other thing is places where I have the lowest pulsar density, if I can fill those in, I can improve my sky coverage, the fraction of the sky that I can see effectively. Finally, there is a question of strategy. I have a limited observing time. Do I survey to look for new pulsars, or do I time the pulsars that I have intensely? And one thing to keep in mind is that new pulsars take many years to make a difference in a pulsar timing array. So I get a new pulsar today, that pulsar doesn't really affect my ability to detect gravitational waves until I have roughly as much data with it as I have with any of my other pulsars. So if my goal is to get the greatest expected number of sources, then I keep in mind that the sensitivity of my pulsar timing array, so this is, if you will, the center, I have virtually no sensitivity to gravitational waves in the direction away from the pulsar. I have a geometric factor that gives me a strong sensitivity to gravitational waves in the rough direction to the pulsar. So this is, in this plot, this is 0, and it's very large as you move out, and then it gets very small over here. So to get the greatest volume of space, I want all my pulsars in the same direction. If my sources are not isotropically distributed, however, then I'm going to want to favor certain directions, and that's going to mean that I want to search, I want to survey in certain directions on the sky. Now, let's suppose that I'm not aiming at beating someone for the Nobel Prize, but I want to, I'm not that interested in being the first to detect gravitational waves, but rather I want to localize my sources so that I can do multi-messenger astronomy. I can do optical follow-ups and the like. If I want to do that, localization is extremely important to me. Detecting a source whose location I have no idea of does not help me. So now if I want to localize my sources, then I want to have a large change in the response with a small change in the location of the source. And that occurs when the angle between the pulsar line of sight and the wave propagation direction is 90 degrees. So I want a pulsar distribution that maximizes the a pulsar distribution that maximizes the number of sources that I will see has a very poor localization capability because I don't have any baselines that are at 90 degrees, that are separated from each other at 90 degrees. It's kind of the worst possible choice to make. I need pulsars. If I got a pulsar out over here, I need another pulsar out over here, 90 degrees away, in order to localize best. So I want pulsars orthogonal to each other on the sky. And that is the looking off the plane for new pulsars, which it's hard to convince pulsar astronomers to do because they say, well, you want new pulsars, we should look where we know there are a lot of pulsars.
Do you just need one out of the plane, or do you need many?
Well, more is always better, but having a couple out of the plane, so, you know, here's one pulsar, having someone here and here would be wonderful. As long as it's a good one here and a good one here and a good one there, then everything else is basically increasing your power and your ability to do things. And so you just need a few to make a big impact here. Now let's suppose that I'm most interested, I'm not worried about multi-messenger astronomy at this point. I just want to do the best job I can with gravitational wave observations. Okay? So maybe then my metric is the ability to measure the polarization of my sources. Polarization tells me a lot actually about the internal dynamics of a source. If I see circularly polarized radiation, I know the source dynamics are non-axis symmetric because that's the only way I can radiate circularly polarized gravitational waves. So I can talk about the Stokes parameters for gravitational waves, and I can define them in such a way that they're entirely analogous to the Stokes parameters in electromagnetic radiation. That is, a specific intensity and then specific intensities in linear polarization and circular polarization. And I can define them in terms of the curvature, like so. Now, for people who are not really familiar with this, one of the ways we talk about one of the ways we talk about polarization of radiation is in terms of the Poincare sphere. So I have a total intensity of the radiation, and I can talk about an intensity in two different linear polarizations, Q and U, and I can talk about the intensity in circular polarization, and there is a nice relationship that the total specific intensity is the quadrature sum of the intensities in the different polarization modes. So this defines, if you will, a sphere. And I can talk about on that sphere a point which is a certain value of Q, U, and V, which is then degree of linear polarization orientation, and the degree of circular polarization. We call that sphere the Poincare sphere. So a natural thing to ask is, in terms of where I think the polarization is, I can talk about an error ellipse or an error volume on the Poincare sphere. And that becomes then a way of mapping how my degree of certainty or uncertainty. Now, if I just talk about the mean power in the mean signal to noise of a source with a fixed specific intensity at the detector, varying by just where the source is on the sky, averaged over the Poincare sphere, I notice something very interesting. Two pulsars, 1713 and 1909, are basically 80% of the signal to noise in the current pulsar timing array. I could throw out all of the other pulsars, not observe them at all, and I would lose no more than on average 20% of the signal to noise. If I look at the error box in as a function on the sky, the volume of the error box for a fixed wave, then I get some interesting patterns on the sky. But again, mostly I'm dominated by two pulsars. These two pulsars happen to have the best timing noise. Can time them in about 50 nanoseconds. Other pulsars, 80 nanoseconds, 100 nanoseconds, 200 nanoseconds, timing residual. It makes a big difference. So even though we're currently timing 30 pulsars, we can throw out 28 of them and concentrate our time on those two pulsars. Or pick a few more and just time them better.
How much is being done in terms of modeling the red timing noise in those two guys?
There's a significant effort in that, and there are several different groups looking at it. There's a group associated with the NanoGrav, the North American Nanohertz Observatory, of which I'm a part. And we're finding for our data set, the noise is coming out as white for those right now. The Australians are finding evidence for red timing noise. We don't yet understand, neither the Australians nor us understand what we're doing differently to come out with two different
But they're comparable observing windows.
Comparable observing windows, and comparable observing cadences, and comparable, they're both roughly about 5 years, looking at 5 years on those pulsars. That is one of the things that we're looking at. The way in which we fold the observations at many different frequencies down to, say, a single TOA on a given day is different, and we're trying to understand that. One of the things that, as I've gotten into this, has been very evident to me is that the noise is not, set aside the question of red, light, or the like. The noise is not very well behaved, on a day-to-day basis. So, it may be technically white, but that doesn't mean it's Gaussian in any real sense of the word. Large outliers, and these are things that have to be dealt with to do that. So, Jim Cordes is involved with NanoGrav, and he, of course, never lets anybody get by without reminding them that you can't make that statement unless you know about the red noise in the pulsars. That's a good question, and it's not one I think is resolved.
But it really, the cool sources, you really beat on them.
Well, and we in fact just got a proposal funded to basically 12 hours of baseband data just sit on 1713 and get as much data as we can on it and really go to town on understanding the noise characteristics there. Okay, let me just move on here. The main thing that I want to emphasize here is that basically right now 1713 and 1909 contribute on average 84% of the signal to noise. If you add the next two most important pulsars, 1855 and 0030, you've got 90% of the signal to noise that you're going to get with the current 30 pulsars that we're timing, and I don't even have 30 listed here. This is kind of the contribution to the signal to noise, and you can see, or fractionally, you can see 1713 is over half of the signal to noise that you can get out of the current array. So there are decisions that can be made in terms of how we observe to really improve our observing, because at least right now it looks like for a while, if we just beat on the pulsars on 1713 and 1909 better, we will be able to improve the timing residual at least until the point where we see red noise. If we're not seeing red noise now, or just seeing the evidence for it, we have some headroom to work with.
So is this the wise thing to do, or should you rather be looking for a third equally good pulsar?
Wisdom is experience. I don't have the experience to say. I would say right now that there is enough time being spent on a number of pulsars that are at 200 and 500 nanoseconds that we don't have to be too wise. We could take half that time, beat on these two, and half that time and devote it to surveys to find pulsars at better positions, and it would probably be a much better use of our time. Okay. And now is when the fact that I signed a form that made that none of you were responsible for what I say here makes a difference. Okay. Basically run into the end, but I'll say just one or two more things before closing. In terms of analysis, what has been done most often, and the kind of thinking that has permeated the gravitational wave community, has been one of predicting, given a source, this is what you will see, and not inferring. That is, given that I see this, what can I say about the source? If we want to do astronomy, it's that latter inference that we want to pursue as our way of analyzing our data. Predicting is taking a shot in the dark. We want to let the gravitational wave observations tell us what we're doing. And that means a different way of looking at the data than has been common and that you will see in most of the literature on gravitational wave detection. Also, you want to focus on the physical curvature, not metric perturbations, for the reasons that we described earlier. Inference is basically a Bayesian way of doing analysis. And Bayesian ways of doing analysis have permeated astronomy over the years, so I don't have to spend a lot of time talking to this audience about just what Bayesian analysis is. Basically, you're computing an odds ratio. Given these observations, what are the odds that I saw something? Or what are the odds that I should bet that the source has certain properties? And once I've computed the odds ratio, then whether I make a conclusion or not it's basically the dirty hairy question. And that is, do I feel lucky? So everybody can choose their own threshold here, but everybody will agree then on what the data is telling you. Right now, we have a number of different ways in which we look at gravitational wave data that are pretty ad hoc, and it's often unclear what question it is that they're answering, and that makes it very difficult to compare. We can't do that when we're doing astronomy. It may be useful when you're doing detection, but not when you want to actually learn something from your sources. This was more or less a question if we had a signal that looked like, say, the flyby of two black holes in a galactic center, say shortly after the galaxies have merged and the black holes are just beginning to find each other. You can expect some hyperbolic or parabolic near passes. Some of them may be close enough that the burst of radiation is in the pulsar timing band. So here's a simulation where this is a signal, and we'll assume 50 nanosecond white timing noise above a tenth of a year and then a red timing noise, a steep red timing noise, below of a tenth per year in frequency, and a strain amplitude corresponding to a peak timing residual of 1 nanosecond, so well below what we can do. We'll take a 30 pulsar array that's isotropically distributed on the sky. This is what the data look like, 50 nanoseconds right here. You're not going to see in any of this, even looking at a particular pulsar, so 30 pulsars here, 1 nanosecond signal peak amplitude, 50 nanosecond white noise over year time scale or over year time scales. You're not going to see it. Nevertheless, a Bayesian analysis that takes into account all 30 pulsars, the log of the base factor is 27. The data are telling you that whatever your initial prejudice is as to whether you saw something or not, you should multiply that by e to the 27 before deciding how to bet. So, in fact, there is strong evidence for a signal here with a lot of pulsars. There's also strong evidence for where that source is. In this particular case, something that's a byproduct of the base factor calculation is the probability where the source might be on the sky. And there is a strong peak over here. This is log probability, by the way. You can infer, you can go further. This is the case of 5 ground-based interferometers, Hanford, India, Japan, Livingston, and the Virgo detector outside of Pisa. It's a weak signal in any individual detector. It's small. If you look at you can estimate the waveform. In this case, I made the waveform a white noise burst in the detector. You locate the beginning of the burst and the end of the burst, and you map the burst very well. The signal to noise in the synthesized antenna is 12, substantially more than in any individual detector if you do the analysis right. We talked about polarimetry, which you can do. This is a map of kind of an error box on the Poincare sphere. It's a very nasty error box for the 5 interferometer LIGO network because of the layout of the interferometers. Even with the India interferometer, you're close to coplanar, and that leads to very elongated error boxes. I'm going to skip here and just move to the end. So you can ask why, why I'm doing this. We don't have gravitational wave observations. Obviously, things will be very different than what I imagine when we do. But nevertheless, I'm motivated by Louis Pasteur, who said that in the realm of science, luck is only granted to those who are prepared. And I think of this as kind of a be prepared exercise, being prepared for gravitational waves and their observations. Thank you very much. I will be here all week, and I would love to talk to you.
Are there any questions now?
I think the point that you say that the localization is best with pulsars at 90 degrees, because laser might claim it's best in the direction of the pulsar because of the polarization moments that give you a quadrupole color.
Mm-hmm. Well, the one way to think about it is if all of my pulsars are in the same direction, in a lot of ways that's like having one very strong pulsar in that direction. And then if I want to localize a source, what I have to have is I have to have something in the response that says that if I was a little bit off in this direction or a little bit off in that direction, that there would be a strong variation in the response. If the response is the same for a source here as for a source here, I can't tell whether it's here or here.
But it's huge because of the control pattern, you get a close to phi dependence.
But it's not in the direction in which I'm most sensitive to. Then by definition, I'm insensitive to small variations.
When it comes to huge variations, there's a close to phi factor in the Eddington formula. Meaning
Well,
the
talk about on
the line of sight has the negative sign in the residual.
Well, if you're going to talk about the Hellings and Downs curve, then you're talking about detecting a stochastic signal.
No, of course, well, we should talk it
Well,
offline.
I think we'd probably talk about it offline.
Can you elaborate on that error box you were showing after the pulsar array discussion? What do you mean by this?
Okay, so let's
flashed by quickly.
Yeah, let me.
Is this a synthesized signal, or is this actually a claim of the detection?
So let's see. No, these are all everything I've shown you is synthesized signals.
Okay.
So first thing, no actual data was harmed in these talks. Let's see. Let me ask a question. Are we talking about? This one, or are we talking about a different one? Different set of figures? Different.
Later, I think.
Oh, it have to be earlier. Let's go. Yeah, let's go.
You had a
set of figures that were something.
You had a scatter plot of the pulsar. No,
scatter plot of the pulsars, right? Okay, let's just let's find this guy. All right, so we're talking about.
No, later. At the very end, tail end of the
I think
pulsar
the one
discussion.
stand where you gave the days odds ratio for
Yes.
7.
Okay.
In that group.
I'm ready. Alright, so let's see, there's characterizing the radiation. Okay. This guy?
Yes.
Okay, so this is basically given the array that I talked about,
Which is an existing array.
No, this was a synthesized array. This was not the 30
Okay, that's what I
nanogram
was missing.
pulsars.
Yes.
Right. Yeah. No, this was if we got to pick basically 30 pulsars isotropically distributed on the sky, all at the same time in residual.
Comparable to the best that they
Comparable
presently
to the
have.
best that we presently have, and I put a weak signal in there. That was
That's
what
the
this
sort of
was.
localization one can do.
Okay. Yeah.
I see.
Yeah.
Is that where the signal is?
In fact, yeah, the signal in this, I can't remember exactly, but it was basically in this in this very dark region over here. So, in fact, it got it right. But of course, one of the things with astronomy that you have to get used to is you never know if you're right. And neither does anyone else.
Any other questions for Sam?
Well, just a general question about detecting the massive black hole interactions with the pulsar. Am I correct in my impression that the estimates of rates that are done don't explicitly take into account the effect of gas torques on the magnets?
Yeah, I mean, the whole question of, how do you approach the last parsec problem, and
Has a huge impact on what you think the rates are.
it has a huge impact on what you think the rates are. And in fact, it looks like there is, when you're talking about orbital periods of one per several years to one per 10 years, which is the interesting pulsar timing band, you can still be driven in that regime, it looks like, by gas.
Right.
It's unclear whether or not
yet in
gas
the
is
final
important. Right. You're not. You can't. The way we understand things right now, you cannot definitively say we are gravitational wave radiation dominated in the inspiral. And that's an opportunity, frankly, because if in fact you can, if you can measure the evidence for the variation in the orbital period over time,
with the detection. And
With the detection,
probe.
then, that's right, then, gas is going to affect that period evolution differently than gravitational wave radiation will. And so there's an opportunity, there's a handle that you have there, and that you can exploit.
I think if there are additional questions, then you can ask the speaker upstairs in your own piece. And we will also have a